Hello. Today we're going to talk about net ionic equations. Net ionic equations are simplified versions of regular equations that only show the necessary components that are changing as a result of the chemical reaction. Let's take a look. So before we get started learning about net ionic equations, there are a few things that we need to keep in mind. Number one, aqueous solutions. Those are solutions that dissolve in water, need to be written as separate ions. We'll talk about how to do that when we see an example. However, there is one exception to that. When we write aqueous solutions for acids, we have to differentiate between strong and weak acids. Behind me, you see a list of 7 strong acids. These are the acids that will dissociate when placed in water. Any other acid, so think acids start with H for the most part, any other acid, any one that's not part of these 7 acids is considered a weak acid. So even though we're going to write it as an aqueous solution, it's going to remain together in the net ionic equation. That is, it will not dissociate into hydrogen ions and anions. The second thing that we need to remember is that some products are unstable. If you were to create, usually using a double replacement reaction, any of the following products, they would immediately decompose into new products that are shown here in green. So for example, if I were to complete a reaction and that reaction resulted in the combination of hydrogen ions and carbonate ions to form carbonic acid, we would not write H2CO3 on the product side. Instead, we would show what actually forms, which is water and carbon dioxide. Let's take a look at our first example. When writing out net ionic equations, we're going to follow the exact same steps that we would when we're writing out traditional equations. In fact, the first 4 steps are what you've learned already. Let's take a look at what those are. Okay, as you can see, the first 4 steps are the normal steps that we would write when writing any chemical reaction that we've learned thus far. So we're going to start by identifying what type of reaction it is. Second, we're going to write out the products for that reaction based on the rules for that type. Third, we're going to identify each reactant and product as either an aqueous solution, a solid, a liquid, or a gas. And finally, we're going to balance the chemical equation using the lowest whole number coefficients. Now on to the new part. When writing net ionic equations, we have to then write what's called a complete ionic equation, which shows how each of the aqueous compounds dissociate in water. Then we're going to eliminate spectator ions. By definition, spectator ions are ions that appear exactly the same on both the reactant and the product side. Finally, we'll rewrite the equation, including states of matter, showing only the ions that remain, the ones that participate in the chemical reaction, forming either a solid, a liquid, or a gas. Let's take a look at this example behind me. In this example, we have a double replacement reaction. So once we identify this as a double replacement reaction, we can look at what our products are going to be. Our first product is going to be the combination of sodium ion and nitrate ion. Sodium is a +1, nitrate is a -1 ion, so the combination will be sodium nitrate, +1, -1. Our second product will be the combination of iron 3+, which we start off with over here, and hydroxide ion. This will form iron 3 hydroxide. Now we can go ahead and look at different states of matter. So first, for the sodium hydroxide, sodium is a group 1 metal. Group 1 metals are soluble, so we're going to write aqueous. For our second, iron 3 nitrate, all nitrates are soluble. So once again, we're going to write aqueous. Taking a look at the product side, we have sodium nitrate. For two reasons, this is going to be an aqueous solution. All group 1 metals are soluble and all nitrates are soluble. Finally, looking at our iron 3 hydroxide product. Hydroxides are insoluble compounds for the most part. Iron is not an exception to that. So iron 3 hydroxide should be identified as a solid. Now we're ready to balance the equation. Looking at our coefficients, we're going to need 3 hydroxides. So I'm going to put a 3 in front of sodium hydroxide. This will require me to put a 3 in front of sodium nitrate, completing the balancing for this reaction. We have, in this case, 3 sodium hydroxides reacting with 1 iron 3 nitrate, forming 3 sodium nitrates and 1 iron 3 hydroxide. Now let's take a look at what our complete ionic equation would look like. So, starting off on the reactant side, I have 3 sodium hydroxides. When they break apart, they're going to separate out into 3 sodium ions plus 3 hydroxide ions. To simplify this, during the complete ionic equation part, I'm going to leave out states of matter, but you can just look to the regular equation just above to figure out what's going on. Continuing, I have iron 3 nitrate. That's composed of 1 iron atom that has a 3+ charge and 3 nitrate ions which have a -1 charge each. Moving on to the product side, I have 3 sodium ions plus 3 nitrate ions. Sodium nitrate, again, is completely soluble. And finally, I end up with iron 3 hydroxide, which is going to remain intact because it's a solid, so it doesn't dissociate into ions when placed in a water solution. Now it's time for step 6, eliminating spectator ions. You can identify a spectator ion if it appears the exact same way on both sides of the equation. So in this example, sodium and nitrate do not change as a result of this reaction. So they should be eliminated as spectator ions. Just like a spectator at a sporting event doesn't participate in the sporting event, a spectator ion doesn't participate in the chemical reaction. It's there simply to balance the charge in the solution. Now, we're ready to write our net ionic equation for this example. So I start by first identifying 3 hydroxide ions, which again are aqueous, plus my 1 iron 3+ ion, also aqueous, forming my FeOH3 iron 3 hydroxide solid. When you are done, you should check for 2 things. Number 1, that the number of each type of atom on each side of the equation is equal to each other. And number 2, that the charge matches up on both the reactant and product side. The charge doesn't have to be 0, but it should be the same. In this case, we do end up with a 0 charge. We have 3 negative ions coming from 3 hydroxides and a +3 ion for iron 3. The right side of the equation has a charge of 0, and you can see from the left side that is also a 0 charge. Let's take a look at our second example. In this reaction, we have ammonium carbonate reacting with sodium chloride. So, in this case, the first thing that we want to do is identify this as a double replacement reaction. Next, we're going to identify what our products are. So in this, ammonium is going to combine with chloride, and sodium is going to combine with carbonate. All ammonium compounds are aqueous. all group 1 compounds are aqueous. In this case, you'll notice that both of our reactants and both of our products are aqueous. You may recall from when we talked about double replacement reactions that when this scenario occurs, there is essentially no reaction. I wanted to show you why that was the case. So, continuing on, if we balance this equation, we'll wind up with the following subscripts. Now, writing our complete ionic equation will result in 2 NH4 plus ions plus 1 carbonate ion plus 2 sodium ions plus 2 chloride ions. On the product side, we'll have 2 NH4 plus ions plus 2 chloride ions plus 2 sodium ions plus 1 carbonate ion. Now it's time to eliminate spectator ions. So first, 2 ammonium ions, 1 carbonate ion, 2 sodium ions, 2 chloride ions. So if you look, all of our ions are eliminated as spectator ions. Thus, no reaction actually occurs when this scenario presents itself. This is why back when we talked about double replacement reactions, we drew the double arrow and said no reaction. You're not going to encounter this very often when writing net ionic equations, because the purpose of net ionic equations is for me to get you to focus on what is actually changing. In this case, nothing occurs. Let's have a look at example number 3. This is another example of a double replacement reaction. In this case, the nickel 2 ion, or Nicholas ion, is going to combine with the hydroxide from sodium hydroxide, forming nickel 2, or Nicholas hydroxide. Our second product is going to be the combination of sodium and nitrate. Again, this is based on charges, so sodium with its +1 charge and nitrate with its -1 charge will result in a 1-to-1 ratio. Now let's have a look at solubility. So on the left side, we have nitrate. So nickel 2 nitrate is going to be aqueous. Sodium is a group 1, thus sodium hydroxide will also be aqueous. On the right side, we have Nicholas hydroxide, or nickel 2 hydroxide. Hydroxides are in general insoluble, meaning they form solid precipitates. So in this case, we're going to write S, since nickel is not one of the exceptions to that rule. Further down, we have sodium and nitrate. That's definitely going to be aqueous. All sodium, sodium's a group 1 compound, all group 1 compounds are soluble, and all nitrate compounds are soluble. Balancing this equation. When we balance this equation, you'll notice that we need 2 nitrates. So we're going to put a 2 in front of sodium nitrate. We have 2 sodiums, so we're going to put a 2 in front of sodium hydroxide, and that will give us the 2 hydroxides we need for nickel 2 hydroxide, meaning both nickel 2 nitrate and nickel 2 hydroxide will have a coefficient of 1. Now, writing our complete ionic equation. Nickel 2 nitrate is going to break down into the Nicholas 2 plus ion plus 2 nitrate ions plus 2 sodium ions plus 2 hydroxide ions. Nickel 2 hydroxide is a solid, thus is going to remain together. Plus 2 sodium ions plus 2 nitrate ions from the sodium nitrate at the end. Eliminating spectator ions. We have 2 nitrates, 2 sodiums. So the only thing that's left are the actual ions that change from reactant to product side, our Nicholas or nickel 2 plus ion plus our 2 hydroxide ions, which come together to form our Nicholas hydroxide. Now let's look at one final example before we take a look at the homework problems. In this example, we have a reaction between ammonium chloride and sodium carbonate. Again, a double replacement reaction. And as a reminder, net ionic equations are going to be most useful when we're talking about either single or double replacement reactions. So in this case, we're going to form a new compound of NaCl, which of course is going to be aqueous, and our second compound, NH4 and CO3. Hopefully you remember that from earlier in the lesson. That's one of those products to be on the lookout for. It's an unstable product which immediately breaks down further into ammonia, carbon dioxide, and water. So first, to show you that the product initially that forms is NH4 to CO3. This is our unstable product. It will immediately decompose into ammonia, which is a gas, plus water, which is a liquid, plus carbon dioxide, which is a gas. On the reactant side, sodium carbonate is going to be soluble. Ammonium chloride will also be soluble. Balancing this equation, we're going to need 2 ammoniums to balance out the carbonate. That gives us 2 chlorides and 2 sodiums. So that'll form 2 sodium chlorides. Finally, when the ammonium carbonate breaks down, remember that it breaks down into 2 ammonias, 1 water and 1 carbon dioxide. Now let's have a look at the complete ionic equation. Starting on the reactant side, we have 2 NH4 plus 2 chloride ions plus 2 sodium ions plus a carbonate ion. Aqueous, so all of this is going to break up into ions. On the product side, we have 2 sodium ions, we have 2 chloride ions, but all of the other products are either gases or liquid, and those will remain together. 2 NH3 plus 1 water plus 1 carbon dioxide. Now, identifying spectator ions. We have 2 chloride ions, those will be eliminated, as well as our 2 sodium ions. That gives us a final net ionic equation of 2 NH4 plus aqueous plus CO3 2 minus aqueous, forming 2 ammonia. Remember that ammonia is a gas, plus water. It's at room temperature, so we'll write that as a liquid. And finally, carbon dioxide gas. Let's take a look at the homework assignment. Looking at the homework assignment, it is broken down into 3 separate sections. In the first section, you're given both reactants and products. You simply have to balance the equation, write a complete ionic equation, and then identify spectator ions, and finally write the net ionic equation. In the second section, where you're asked to identify products first, then balance the equation, write a complete and net ionic equation. And then finally, in the third section, you are asked to, using words, convert that to chemical formulas, predict what the products are, and then finally write a complete and net ionic equation. It starts off easy and then gets progressively harder. I'm asking you to complete the next 3 problems. So after we go over the examples in each section, to complete the next 3 problems in each section for homework. You do not have to complete every one, but I will post the answer key, which will show the correct answers for all of the problems on the assignment. Let's take a look at problems 1 and 2. In problem number 1, we have a really simple equation where all of our coefficients end up being 1s. In this case, we can jump right into the complete ionic equation, which will look like this. Na plus Cl minus plus AgC2H3O2. We're not going to break that up because it's a solid. On the product side, we have Na plus C2H3O2 minus plus AgCl. In this case, there's only one spectator ion that can be eliminated, the sodium ion. All of the other ions appear different on both the reactant and product side. So our final net ionic equation is Cl minus aqueous plus AgC2H3O2 solid forming C2H3O2, our acetate ion, plus silver chloride, which is our solid precipitate. Notice in this example, we don't end up with a 0 charge on each side. Instead, we have an overall -1 charge on the left side and a -1 charge on the right, which is completely fine. As long as they are equal to each other, they don't have to add up to be 0. All right, taking a look at problem number 2. First thing I want to do is balance the problem. So I have 1 calcium on the left, 3 on the right. So I'm going to put a 3 in front of calcium hydroxide. I have 2 phosphates on the left, or excuse me, on the right. So I need 2 on the left. So I'm going to put a 2 in front of the phosphoric acid. And finally, if I look, I have 6 hydroxides and 6 H's. That's going to allow me to produce 6 waters, leaving us with a coefficient of 3, 2, 6, 1. Now let's take a look at our complete ionic equation. On the left side, we have 3 calcium ions plus 2 times 3, or 6 hydroxide ions, plus, now, in this case, we have an acid. It's phosphoric acid, which is a weak acid. So remember the rule, even if we have something that's aqueous, if that aqueous compound is a weak acid, we're going to keep that together. So it is not going to separate into H plus PO4 3 minus ions. It's going to remain together as H3PO4. On the product side, we have 6 waters. That's going to stay together because they're a liquid, plus our calcium phosphate solid, Ca3PO4 In this case, if you notice, we don't have any spectator ions. Yes, our calcium ions are aqueous, but they don't appear the same way on the product side. Same thing with our hydroxide. On the reactant side, they can be written as aqueous, but on the product side, they appear differently. In this case, this formula serves as both our complete and our net ionic equation. On to section 2. Let's take a look at problems 9 and 10. Notice, in this case, you're not provided with the products. So you're first going to have to identify the type of reaction. In both cases, we have a double replacement reaction. And now you're also going to have to predict products. So we have lead 2 that's going to combine with sulfate to give us lead 2 sulfate, PbSO4, plus a second product, which is the combination of sodium and nitrate. Remembering, of course, sodium and nitrate are both +1 and -1 ions. We need just one of each. Lead 2 sulfate. Sulfates in general are soluble compounds, but lead 2 is an exception to that. So that's going to be a solid. Sodium nitrate, that's made up of a group 1, that's always soluble, and a nitrate, those are always soluble. So the next part is to balance this equation. Balancing the equation, we have 1 lead, 2 nitrates, so we're going to put a 2 in front of our sodium nitrate, two sodiums. We have two sodiums in sodium sulfate. So this will get a 1, a 1, and a 1. Now let's have a look at our complete ionic equation. So in the complete ionic equation, we have lead 2 plus 2 NO3 minus ions plus our 1 sodium sulfate. That's going to break down into 2 sodium ions plus 1 sulfate ion. On the product side, we're going to keep together our solid precipitate, lead 2 sulfate. We're going to break apart our sodium nitrate into 2 sodium ions plus 2 nitrate ions. Eliminating spectator ions, we are going to get 2 nitrates on the left, 2 nitrates on the right, 2 sodium on the left, and 2 sodium on the right. Those will be gone. So our final and net ionic equation is lead 2 plus, which is aqueous, combines with sulfate ion, which is also aqueous, producing lead 2 sulfate, which is our solid product. Notice 2 plus, 2 minus, 0 charge total on the left, 0 charge total on the right, 1 lead, 1 lead, 1 sulfate, 1 sulfate. Let's take a look at question number 10. We have silver chlorate, which is aqueous. So the rule says that most chlorate or all chlorates are aqueous. And of course, potassium chloride is a group 1. That's going to be aqueous. The halide portion of it is also going to be aqueous. So our products are going to be KClO3 plus 1 minus 1. That, of course, is going to be aqueous, plus our second product, AgCl plus 1 minus 1, which is going to be our insoluble halide. So halides, like chloride, are insoluble with the exception of silver, lead 2, mercury 1. All right, taking a look at this expression, plus 1, minus 1, plus 1, minus 1, all the way down. That means all of our coefficients are going to end up being 1. And now we can go ahead and write our complete ionic equation. So we have Ag plus ClO3 minus 1 plus K plus Cl minus goes to form K plus chlorate ion plus our AgCl precipitate, which we're going to keep together. Spectator ions include chlorate, potassium ion, leaving us with just silver and chloride. So our final equation here is going to be silver, which is aqueous, plus chloride, which is aqueous, forming silver chloride, which is our solid. We're almost there. On to section 3. In section 3, remember that we're starting with words instead of chemical formulas. So that makes it a little bit more challenging in that we have to convert from words to formulas before we can continue with our reaction. Let's take a look at example number 1. We have mercury plus sulfuric acid. In the homework assignment, it tells you to use mercury 1 as the ion of choice on the product side. So we're going to form mercury 1 sulfate and if we have a look at our activity series, the other product from this is going to be hydrogen gas. Looking at the chemical formulas, we have mercury, which is a liquid, reacting with sulfuric acid, H2SO4. Remember that we write acids as aqueous solutions. On the right side of our equation, we have mercury 1 sulfate. Remember that mercury 1 is Hg2 with a 2 plus charge. Sulfate is SO4 2 minus. So we wind up with the formula Hg2. The 2 plus and 2 minus cancel out. So we have sulfate plus hydrogen. And again, hydrogen is a gas. Mercury is a liquid. Sulfuric acid is a strong acid, so we're going to break that up. And then finally, sulfates in general, soluble. However, mercury 1 is an exception, in which case we're going to write solid. Filling out the rest of this, we have 1 mercury, 2 mercuries, so we're going to put a 2 in front, 2 H's, 2 H's, 1 sulfate, 1 sulfate. So the remaining coefficients will all be 1. Looking at our complete ionic equation, we can't do anything with the liquid mercury, so we have 2Hg, we'll keep that as a liquid, plus sulfuric acid. It is one of our 7 strong acids, so we can write that as ions. H plus ion, which is aqueous, plus HSO4 minus ion, which is also aqueous. On the product side, we keep everything. So we have mercury 1 sulfate and hydrogen, solid and gas, so we don't have to write any ions here. So we have Hg2SO4, solid, plus H2 gas. In some cases, our complete and net ionic equations are the same thing. That is the case here. There are no spectator ions. There are no ions that appear the exact same way on the product and reactant side. So there's nothing that we can eliminate here. Now let's have a look at our final example. We have calcium carbonate reacting with sulfuric acid. So putting these two pieces together, we're going to get calcium sulfate as one of our products. And the hydrogens from sulfuric acid and the carbonate ion will give us carbonic acid, but wait. If you remember, carbonic acid, H2CO3, that's one of our unstable products that never gets written on the right side of the reaction. So instead, we're going to write this as water and carbon dioxide. Writing out the chemical formulas, we have CaCO3 plus H2SO4 going to form CaSO4 plus H2O plus CO2. Now let's identify their states of matter. We take a look. Calcium carbonate, that's like chalk. It's an insoluble compound. We interact with some sulfuric acid. Remember, acids are going to be aqueous. Calcium sulfate. Sulfates are soluble in general, but calcium is an exception, so that's a solid. And since this reaction will be occurring at room temperature, water is going to look like a liquid. Balancing this equation, writing out our proper coefficients here, we have 1 calcium, 1 calcium, 2 H's plus CO3 is going to be H2CO3, which breaks down into 1 water and 1 carbon dioxide, and finally 1 sulfate and 1 sulfate. So all of our coefficients in here are 1. And finally, wrapping this up, our complete and net ionic equation are going to be the same thing. So we're going to include states of matter as we go through this. We have calcium carbonate, which is going to remain together as a solid, plus sulfuric acid, a strong acid. So we're going to break this up into H plus ions plus HSO4 minus ions, forming calcium sulfate solid, plus water as a liquid, plus carbon dioxide gas. Okay, that about wraps it up. If you have any questions, please send me a message through Schoology or send me an email, and I'll be sure to get back to you. Thanks, everyone.